Okay, with self-introduce, since you're already up there and.
Sure.
Ready to go.
Did you want to? Nope. Okay. Hi, everyone. I'm Joel Morgan. I'm a senior solutions architect at Amazon Web Services. I cover the University of Washington. A solutions architect is a technical resource for customers like you to talk with someone at AWS, everything from answering simple questions all the way up to designing large infrastructure architectures or application migrations, things like that. I do work a lot with research. I've covered the University of Washington for a few years now, and I've been at AWS for 11 years, which is 1 million in cloud years. So, today, I'm going to talk to you about other ways of getting compute done on AWS. So there's, of course, the standard, here's a virtual machine, it's running an Intel processor. You SSH into it or RDP into it, and get your work done. Then we have GPUs. So, of course, NVIDIA GPUs, we do have AMD GPUs also. If you're doing something that needs to be GPU accelerated, there are options there too. But beyond that, we have other ways of doing compute on AWS, different hardware. So when I say different ways of doing compute, of course, there's traditional virtual machines, there's container infrastructures, there's serverless computing. What I'm talking about here is the actual machine that's doing the job. And we have, of course, with EC2, there are hundreds of different EC2 instance types. An instance type is a combination of CPU and RAM that's available to your instance. But beyond the typical x86 processors, we have accelerators to help with machine learning and AI, and we have alternative CPU architecture also. So that's what I'll be talking about today. And also, please feel free to ask questions. In presentation mode, I'm unable to see the chat, so feel free to come off the mic, turn off mute, and come on the mic and ask a question. So EC2 accelerate. We'll start with accelerated instances. So EC2 accelerated computing instances, they use hardware accelerators or co-processors to perform some functions like floating point number calculation, graphics processing, or data pattern matching more efficiently than is possible running only on CPU. So these instances enable more parallelism for higher throughput on compute-intensive workloads. If you require high processing capability, you'll benefit from using accelerated computing instances, which provide access to hardware-based compute accelerators such as graphics processing units, GPUs, field programmable gate arrays, or FPGAs, and AWS custom accelerators such as Inferentia and Training. So here we go with hardware accelerators, higher throughput because they're usually more purpose-built than running something on a general use CPU. Higher efficiency. So if it's meant to do something, if hardware is designed to do something specifically, it can be more efficient both in time, but also in cost. Sometimes we have things which I'll get into that may be faster or only slightly faster, but the price performance ratio is much higher. So you can get a lot of work done for less money. And we have many different types of accelerators that I'm going to talk about today. So we have, of course, GPUs, FPGAs, and we have some custom ASICs or application-specific integrated circuits that are all available to you. So to address the specific needs and the general customer requirements around faster time to train, lower costs, and higher performance, we've been building out our portfolio of hardware accelerated instances. So we have a broad portfolio of accelerated computing instances, including FPGA, GPU, and AWS custom accelerators. And custom accelerator-based instances are designed as performance and cost-optimized training and inference in the cloud. So these include AWS Inferentia, and AWS Trainium accelerator-based instances. The other instances are based on GPUs and other hardware accelerators from NVIDIA, AMD, and Intel. So we can look at this chart here. If you're unfamiliar with AWS, our EC2 instance types usually have a family and then a generation. That's what the letter and the number are. So the G series and the P series are our GPU accelerated EC2 instances. And the number is the generation of them. So for example, the P5 has H100 NVIDIA GPUs on it. The P4, I don't know why this says preview, I should have edited that. Those are in production, you can use them, have A100s. The G series also have NVIDIA GPUs. These are typically more for actual graphics processing, while the P series are for computation by the GPU. So think AI, machine learning, things like that. We also have specific accelerators for machine learning and AI. So Gaudi accelerators, I won't talk too much about them, but they are part of our portfolio. Our deep learning instances, so the DL1, Inferentia, which I'll talk about in more depth later. There are two generations of Inferentia. Those are custom built by AWS for inference. We also have Trainium, which is the other half of that equation, where customized silicon for inference. And then, of course, we have our FPGA-based instances, which have a Xilinx FPGA built into them. So if you wanted to write your own Verilog and create essentially your own chip, you can do that within an EC2 instance. Yeah.
I'm sorry, I might be wrong, but is the Intel accelerators like kind of related to the Microsoft like AI PCs? Is it built on like some of the similar technologies?
The Intel accelerators are specifically for deep learning, is what they're built for. They weren't really built like they were built by Intel. I'm sure Microsoft and Amazon and everybody had some consultation with them, but no, they're not like specifically Microsoft's. Yeah. Accelerated computing workloads. Fire truck going by if you hear it. So we have our machine learning, things like our Trainium, our P5s and P4s, our Inferentia, and the G5s and G4DNs for machine learning inference, HPC. So if you have a GPU accelerated workload in high performance computing, then that's when you're looking at your P4s and P5s. I should also say we have HPC specialized instances that do not have GPUs. So if you have a CPU based workload, we have some purpose-built HPC machines. I won't talk about today because at the end of the day, those are just x86 compatible CPUs, but they're clustered in a more advantageous way for HPC workloads. And then graphics themselves. So if you're doing rendering or like it says transcoding, even streaming, things like that, that's the Gs. So in this slide, you can see the Ps and the Gs. They both have NVIDIA accelerators in them, but that's why there's two different. The G series is more for you're doing something visual with the GPUs. So purpose-built accelerators for AI. So we've been investing in the most price performance infrastructure for machine learning, so you can really scale. Over the last 5 years, we've been investing in our own silicon to push the envelope on performance and price for demanding workloads like ML training and inference. And our AWS Trainium and AWS Inferentia chips offer the lowest cost for training models and running inference in the cloud. So this ability to maximize performance and control costs by choosing the optimal ML infrastructure is why leading AI startups like AI 21 Labs, Anthropic, Cohere, Grammarly, Hugging Face, Runway, and Stability AI all run on AWS. So, there's a ton in here, but basically you can get 40% better inference price performance than other comparable EC2 instances for low cost inference. So versus using GPUs with one of our P or G series, you can use our Inferentia chips, which can give you up to like a 40%, essentially 40% less to get the same amount of work done.
So if I were to spend $1 on an EC2, then what would I be spending on an Inferentia 1 and an Inferentia 2?
So with just for nomenclature, they're all EC2 instances, but these are additional accelerators that are available to it.
Right.
It's like the P series and the G series, you're using, let's say you have the P5 and you're using H100s, NVIDIA GPUs. Well, if you're doing inference, you can use an EC2 instance with an Inferentia chip, and it is significantly less expensive. Same thing with training, with Trainium, which is custom built silicon for training. So if you were doing that, you could train your model using that chip instead of the GPU, and it can be significantly less expensive. So, for example, I was looking at earlier today, like a Trainium, an instance with the Trainium chip in it is about $22 an hour for on-demand pricing. While a P5, now granted, it's not exact apples to apples comparison, but like a P5 is $90-some per hour. So if you're, and we'll get into it later, but if you're writing NVIDIA CUDA code, you're getting to that hardware level, of course, use a GPU accelerated instance with an NVIDIA GPU. But if you're using something like PyTorch or MXNet or TensorFlow, you can use, which I'm kind of jumping ahead here, but you can use our Neuron SDK to make your code work with our Inferentia and our Trainium chips. So for ML inference, our Inferentia 2 instance, that's our newest one, the second generation of Inferentia. So ultra high speed connections, connectivity between accelerators. So raising the performance of our previous generation by three times. So 3x higher than first generation. And 4 times larger total accelerator memory, or 4 times higher throughput than the initial generation. So our second generation is essentially 4 times faster in every way. They deliver up to 40% better price performance than comparable. So if you were to run that job on a GPU, an NVIDIA GPU versus one of our Inferentia chips, it could be 40% less expensive. So we have, I know there's a lot of text and it's probably hard to read while I'm talking about it, but I'll make sure everyone can get slides afterwards. Of course, we have, and A100s and H100s, and then we have the G series, so that's the T4. So we have the P5s, and which are the H100s, the P4s, the A100s. These are our Trainium. Training, this is for deep learning. Those are the Intel Gaudi accelerators. And you can see things like, beyond just it has a GPU, the P4s and P5s are slightly different architecturally than other EC2 instances in that they're an ultra cluster. You would treat them as if they are a single EC2 instance, that they're one machine, but behind the scenes, hardware-wise, they are a cluster of multiple hosts. 3,200 gigabits per second networking, 80 gigabytes GPU memory for the P5s. So as I mentioned, this is what I meant by ultra clusters. So when you pick a P4 or P5, those are our EC2 instances that have NVIDIA accelerators in them. This is really what you're getting here. So non-blocking petabit scale networking between them. So it essentially acts as one machine. There's GPU to GPU, direct GPU to GPU communication. So you can see all the stats there. If anyone wants to try these out and talk more about specifically the P4s and P5s, I'm happy to do that.
Are you referring to this as, I see the word tranium in this diagram, but you're also using the term GPU. So are you considering a tranium chip a class of GPU?
It's an accelerator in that it's something else in the machine that is more purpose built for than the CPU, but there is still a CPU. So our Trainium machines and our P4s and P5s, while one has NVIDIA accelerators and the other has has AWS built accelerators in it, they're this kind of infrastructure. Okay. I'm just going to kind of skip over the graphics stuff unless someone on the call has a burning desire to talk about it. This one is interesting. There's custom silicon by Xilinx for video transcoding. So if you have a lot of video to transcode, there is hardware acceleration for that too. And I have done it. I've messed with these before, and it's like crazy fast, 10 times faster than if you were running it on the CPU. Yeah, I should have edited this. This is basically the same slide. I don't know why I put it in here twice. Yeah, of course, classic. These are the people using it. I'm sure you're not at all surprised at them. The thing about these slides in general at AWS is that these are only public references. So there are many, many, many research use cases across the US, but we can't talk about them unless somebody says, hey, I want to be a public reference. So that's why you typically have these commercial entities up here instead of this lab at this university. So this is basically a generic slide that we put at the end of everything, but these are the things that we can help you with. It's not really specific to our accelerators, but this is what the things we can do. So this is me. I'm happy to talk to any of you. It's free to talk to me. I'm not a salesperson. We can also, there are opportunities for proof of concept development where we can help support that with credits and things like that. One thing that, for whatever reason, is not in this version of the, apologies, this version that I downloaded is to use Inferentia and Trainium. There is what we call the Neuron SDK. So if you're using, let's say, PyTorch, that's usually the most popular, look at the documentation for our Neuron SDK, see what you need to do to adapt your code to it, and then you can use these custom-built accelerators for inference and training. It's not magic, it's not drag and drop, but it's not a huge lift. I did have slides for that, but they're not in this version for some reason. So long story short, custom silicon that can save you money. I'm not coming up here and saying, oh, our custom hardware is so much faster than an NVIDIA GPU. No, that's not the purpose of it. The purpose is, all right, I have a machine learning workload. I'm doing training or I'm doing inference. Can I do it cheaper than paying for very expensive GPUs? So GPUs are still yes, they're used almost exclusively these days for AI and machine learning. That's not really what they're built for, right? They are still graphics processing units. So it is a different way of working than a CPU works, but they're still general enough. While Trainium and Inferentia, the chips we've developed, are specifically just for inference, just for it, right? It doesn't have to do anything else. And it was built, so it was built for that. It was built to be less expensive than a GPU. So any questions on that while I get my the next step? We have, this one wants to do this, but let me drag it over here. Oh, PowerPoint. Why don't you want to do presentation mode? Okay, so any questions about our other accelerators? So Trainium, Inferentia, FPGAs, anything like that?
So I guess it'd be good to have a sense of, okay, I've decided I want to use Inferentia. So I'm going to go on to, let's say I'm going to be a console worker. I'm going to go on the console. I'm going to start up just to the EC2 wizard, and I'm going to select the Inferentia pipe. And then from there, is there anything, I think you were mentioning to go Neuron SDK, or
Yes.
that's the key to being
Address
able to take my existing, so let's say, NVIDIA GPU adapted workflow and fixing it into this Inferentia EC2.
Correct. Correct. So from the EC2 side, it's the same as launching any other EC2 instance.
Yeah.
So you just pick, oh, I want the training, right? And if your code is abstracted, you're not writing to the hardware level.
Let's say I'm writing PyTorch.
If you're writing PyTorch, then yes. Then this is what you're looking at. Say, okay, great. Of course, you'll want to look into this before you launch your EC2 instance, so you know what you're getting into, and rather than having an instance running. But here's some samples. Like Stable Diffusion, right?
Okay, so I'm installing the Neuron version of Torch.
Right. So then here's an example of what a Stable Diffusion would look like for the Neuron SDK.
Okay, I see the critical line just scrolled off the screen there and Torch Neuron X.
Yes.
Line 22.
Yeah, yes.
So there's a change in my Python code that will have to realign my job with the Neuron X version of Torch. Okay, got it.
Yeah, so then it will address the custom silicon with training.
Yeah. Cool.
Okay. So if you were like I mentioned before, if you were writing CUDA code directly address an NVIDIA GPU, that's different. That would take a lot more work and may or may not be beneficial. But if you're using PyTorch, as you can see, we have plenty of documentation and examples of how to do that.
Cool. Thank you.
And there's lots of tutorials and stuff. So you may be able to find something close to what you're doing. But yeah. Next, we could talk about a different CPU architecture in our AWS Graviton processors. Okay. I'm going to be, anyone who's looking at camera, I'm going to be doing a lot of this because I don't have the screen mirrored. But this is talking about our compute platform. Of course, we have GPU, we have memory intensive. So if you have a workload that may not need a ton of CPU, but it definitely needs a ton of RAM, you can get that. General purpose, compute intensive, all sorts of, basically any workload you can think of, there's an EC2 instance type that will work for it. So here's our different processor architectures. Now, this is not accelerators like the GPU or our custom ASICs in Trainium and Inferentia or an FPGA. This is the CPU, Central Processing Unit. This is the architecture of them. Most of them, the vast majority of ours, have Intel Xeon processors of various generations. That's the CPU available to most of our EC2 instances. We also have AMD-based instances, so also x86, but they're AMD EPYCs instead of Intel Xeon. And we tell you, it's you'll see in the name of an EC2 instance type, it will have an A, say, oh, that's an AMD. Now, whether that matters to you or not, I don't know. If you were writing something to a very specific Intel instruction set with an Intel compiler, then that may make a difference to you. I've found that that's few and far between, but it does happen in the research world where you have some application that has to be compiled in an Intel compiler for an Intel chip, even if you have another x86 processor, it doesn't like it. So like our P series that I was talking about previously, those are actually AMD CPUs. Then what I'm going to talk about most here is Graviton. So I'll kind of skip over that and address the last one. So Apple. When these were launched about 3 years ago, everyone was very excited. I have to pour water on everyone's excitement, and these are not remote workstations or anything. There is no graphical user interface. It is specifically for compiling and testing code if you're writing code for Apple Silicon. So if you're a developer, you're writing something that needs to be compiled on Apple's M chips, then you can absolutely do that. If you're thinking, I'm going to get OS 10 remotely in a virtual machine, that's not what they do. So, apologies. Our Graviton processors. So, AWS Graviton processors are built by us, right? So we acquired a company many years ago that designs processors of many types, and we decided, you know what? Let's try and make our own chip that will be much more power efficient and will be a better price performance ratio for our customers. Now, what it doesn't come right out and say here are these are ARM architecture chips, right? So these are not Intel x86 based. These are, for comparison, much more similar to the processor you have in your phone, or if you have one of the newer Apple computers that has their M chips. So these are ARM-based processors. Without getting into the history of ARM, they started out life as a RISC processor, reduced instruction set, which is different than CISC processors. But I mean, if you're in modern architecture, they're not super different anymore. Anyway, so our first generation, 45% cost reduction if you took the same workload on an Intel-based EC2 instance and a Graviton-based EC2 instance, it was 45% cheaper to run it on. So they were great, and we iterated on it because it worked well, and people seemed to like it. So Graviton 2, 40% better than even Graviton 1, and then Graviton 3 was a pretty big leap in that, so 25% better compute performance than Graviton 2, and better floating point performance than Graviton 2. And then Graviton 4 has been out for a little over a year, I think now. So it's now 30% better than even the previous generation, but 50% more cores available and 75% more memory bandwidth than Graviton 3. So these, while they're very good, you wouldn't get like massively multi-core machines, right? With Graviton 4, as you'll see later, these are serious multi-processor, multi-core machines. And fun note, it doesn't say it in here, but these things are huge. I hadn't seen one in person until 2 years ago, and yeah, they're not that big. I was harassing one of the people on the Graviton team about when we'll be able to buy them at retail. He said, well, never, they're gigantic. Yeah, whenever they show them internally, it's just, okay, well, there's no reference, or it's in a chassis, and it's like, okay, well, that doesn't look that big. No, they're big. Anyway, that doesn't matter. I just thought it was interesting. So, why would you go ARM? Is because with Graviton specifically, the price performance ratio is higher. We're not saying that, oh, you should port your application to ARM instead of x86 because it's faster, but it is more power efficient. It's less expensive for us to make them, so you benefit from those efficiencies. Yeah, and this is a big thing. So 60% less energy than comparable EC2 instances. So if you take something of, all right, well, this has this many cores and runs at this clock speed, and this Graviton instance has this many cores, runs at this clock speed, the Graviton is going to use a much less electricity to run. So previously with our Gravitons, if you ever played with them, and you played with them a couple of years ago, you would see it was pretty limited in the instance types, right? Our modern Graviton 3 and Graviton 4, you have a wide variety of instance types. So once again, an instance type is that virtual machine. When you're launching an EC2 instance, you get to pick your instance type, and that is the amount of CPU and RAM available to it. Now, notice I'm omitting storage, and that's because storage is slightly abstracted from it in that you could have a very small EC2 instance with a ton of storage with attached EBS volumes. You could have a very powerful EC2 instance with tons of CPU compute power, but very small. You may not need that. So that's why we separate that. So if you have a workload that needs a ton of storage space, but doesn't need a lot of compute, you don't have to get a giant instance just to have it. So anyway, so we have different families. So general purpose, compute optimized, memory optimized, accelerated, storage optimized, and HPC optimized. And what this means is the machines that these are running, these virtual systems are running on, are configured differently. They may have different hardware, purpose-built for different things, right? The general purpose is exactly what it sounds. It's like, all right, well, I don't have any special needs for this application. I just need, this much RAM, this much CPU, great. Many different types there. And the G means Graviton, just so you know. Compute optimized simply means we've given you more virtual CPUs, but not necessarily increase the amount of available memory or CPU heavy workloads. So why pay more for more RAM, like if you don't need it? That's why we have these different families. Compute optimized. Memory optimized is the inverse, right? Like especially database or database-like applications, you may need a ton of memory, a ton of RAM to run the application, but you may not need a ton of virtual CPUs, a ton of cores, right? That happens. Accelerated computing is, so when I was talking before about computers with accelerators in them, those were all, of course, Intel-based. So all of the P series, the G series, and the Inferentia and Trainium CPUs in those are all x86. They may be Intel, they may be AMD, but they're all x86. We do have Graviton-based instances that have a GPU in them. So if you have written an application or ported an application that will run on an ARM CPU, but still needs a GPU, I mean, honestly, these are mostly for gaming, like mobile game developers, because you need a real GPU, but you're running on an ARM CPU. Storage optimized has some advantages to if you have a really high data throughput, something that's reading and writing from the storage very, very quickly. We have some that are purposely built for that. And then we have HPC. If you want to run a high performance compute job, but you have ported your code to ARM to take advantage of the cost difference. So we do have instance types that are built for an HPC workload that use Graviton process. So we have many different services that are compatible with Graviton. What I mean by that is, for example, you can run your Amazon RDS instance on Graviton. You can that is a choice. When you're picking your instance type, you can say, okay, I want my Aurora database to run on Graviton. Same thing with like Fargate, which is our serverless container service. So you can say, I have a container, I want to run this, I don't want to spin up, I don't want to deal with the headache with Kubernetes and have a whole cluster just to run my container. Fargate will do that serverlessly. You can say, all right, well, I have ported my code to run on ARM, so I can run it on Fargate. That's one of the options. Same thing with ECS and EKS. And SageMaker is our machine learning and AI suite of tools. It's a whole studio. It's not one specific thing, but it has the ability to use ARM-based instances for its compute. Yeah. So seamless, what we mean by this ease of adoption is, let's say I want to run an Aurora database, like I mentioned earlier. You're not writing code for it, you're just getting a hosted database, right? You can pick Graviton as the processors for the instances that are running your database. You don't really have to do it. You're not writing code to it, you're not porting code, you're just saying, hey, I want a database, right? From your application side, talking to the database, writing a SQL query, it doesn't matter. It doesn't know or care what the CPU it's using on the servers that are running the database. So things like that. Yeah, like it typically just works. It typically does just work. If you're spin up an Aurora Postgres database, your application that's running using that doesn't care. Right? It's an ARM process. It never gets to that level. So Lambda. Lambda is our serverless compute where you write a function and then you invoke that Lambda function, whether on a schedule or whether it's triggered by some service or it's fully triggered through an API call. Lambda runs your function and then goes away. So if you have a piece of code that can run in under 15 minutes, Lambda is perfect for it. Yeah, you ever talk about Lambda, I'm happy to talk about Lambda in depth in the future if you'd like. But you can, we say it's pretty easy to port your code in your Lambda function to run on a Graviton-based Lambda function. You do have to port your code though, because it was probably written on an x86 processor. Like if you were to write that on your write code on your Surface, you'd have to recompile it to run on yours, same thing, even though it is an ARM process, not the same process. Yeah. Linux interpreted languages, there's a lot of support for ARM-based systems. There's many, all the major distributions have an ARM version. So if you wanted an EC2 instance that was running Ubuntu on Graviton, you can absolutely do that. Many tools have been compiled already. So there are repos out there that have ARM versions of those applications. It's honestly fairly reminiscent for anyone who's old enough to remember this of the PowerPC days. It's like you could have, PPC version of it or the Spark version of it to the Sun, and the x86. More involved are if you have dependencies, like you're writing something in like C++, yeah, you've got to get some other libraries, learn how to recompile it. If you're making very lower level calls to the CPU, yeah, that's going to have some re-engineering as opposed to just porting code. Yes. Some work, high reward. Yes, you can refactor your .NET application to use an ARM processor. You can migrate it to Linux on, that's basically what we're saying. It's you migrate your .NET application to Linux using the .NET Core on an ARM-based.
Can you remind me of the NoSQL database service at AWS?
DynamoDB.
Dynamo.
Yep.
Okay, so I don't see that in the workload under the top there.
Yes, I don't think that's available yet.
Okay, so that's not there. But what you seem to be telling me, I'm just repeating this back so we can sort of confirm that it's true, is if I went and set up an RDS system on without thinking about it, never selected any G for Graviton, and I got a bill at the end of the month for $100. And then I'm like, whoa, wait a minute, let's try this with a Graviton. And I started over and I did everything exactly the same. My bill at the end of the second month is going to be $50.
Yes.
And there's absolutely no difference to me in the experience. So I'm a complete idiot if I stay with the $100 version. Right? It's okay. We can call me an
It
idiot.
is more cost efficient. Yes. Yes. And you would have to really do nothing.
Okay. So this seems to me like a kind of a easy to miss.
Yeah.
Cost savings opportunity.
Yeah.
Oops, sorry.
Yeah.
Oh, it's Jim Fong.
Hi.
Hey, Jim.
Now, I will say that we have RDS out there. We have Aurora up there. It is not available for every database engine. So if you were running an Oracle database on RDS, not available. They don't compile it for ARM. Same thing with Microsoft SQL Server. You can't run a Microsoft SQL Server RDS on Graviton.
On Graviton. Okay. But this is obviously, this needs to register for those of us concerned with saving a dime on the cloud.
Yeah. Yeah. And in fact, once I get through the slides, I'll bring it. Show you.
Yeah.
Hi.
What flavors of SQL will be supported on Graviton?
Yeah. So MySQL and Postgres, and I have to see what else.
MariaDB.
I think so, but I want to confirm it. Like I said, I'll get through the slides and I'll bring it up and confirm it.
Okay.
But I think so. Yeah, I haven't launched one of those in a long time. Yeah.
Okay.
Yeah. And same thing with like OpenSearch or like EMR is our Elastic MapReduce service, and those you have the option. Like, hey, just you're running this like EMR uses Hadoop or Spark or Pig or Hive. Those have been compiled for ARM, so they'll work on Graviton instances. I don't know what buzzing is.
It's probably.
These Graviton preprocessors, this is really getting into how these CPUs work. We have limited time, so I won't go too deep. If you're a scientist, and you really like to know deeply more about the structure of our Graviton processors, I'm happy to provide. Just let me know, send me an email, and I'll get you information. We can meet. But yeah.
I apologize for being late,
No, that's fine.
but I will go ahead and ask like the what is this rated for type of question. Have these had encryption or an information security review for like HIPAA compliance? or things in like very high, like sensitivity and volume
Yeah, they're HIPAA
eligible.
Yeah, we never say HIPAA compliant because we're not running the workload.
Right.
You're running the workload on us, but we have HIPAA eligible services, meaning if you implement your, whatever you're running correctly, it is HIPAA compliant. Yeah, sorry, I have to be very
I understand.
specific and nuanced with saying that, but yes, you can run a HIPAA compliant workload on Graviton. Yep. In fact, I think there's. Yeah, so our C6I means Intel, so that's an x86 based processor. Our C7G, which means it's the compute optimized 7th generation Graviton instance. We have physical cores here, where I know for years I've been coming in here saying a virtual CPU, a vCPU is actually a thread on a single physical core. And I also give my little speech about if you don't, don't turn off hyper-threading as a knee-jerk instinct reaction. If you know for some reason that your application runs better by turning it off, fine, but the vast majority of applications run much better with hyper-threading on. Okay, now that I know with that little speech, a vCPU really is a thread, right? It is not a core, a physical core. So you see a C6I has 64 virtual CPU that has 32 physical cores. Just to make life confusing, we have said that the vCPUs for Graviton basis are physical, right? So you can see here processor execution resources. If you're running something on virtual CPU 2, your application is running multi-processing, multi-threading, whatever. It's running on this second CPU. It's actually running on one physical core with another process that might be running VC. Now, here it is running on its own. That's cool. This is not, I don't know why they pushed this so hard in this slide deck, but this is not why they're more efficient. They're more efficient because we built them to be. But yes, vCPUs on a Graviton are physical cores.
Who would need to know that?
Nerds.
Yes. We do have
I'm sorry. This is very rude.
we have customers who do like electronics design and stuff. There are some workload. I'm trying to remember. There was some workload in computational fluid dynamics where it was written to a specific Intel instruction set, and you had to turn off hyper-threading, right? So, if you tried to run it, because everything on your laptop, your phone, it all runs for over 2 decades now. That's just been the norm, right? But in the cloud, we say virtual CPUs because that's what it really performs like. That's what it acts like, but it's not a physical core. And Intel's been doing that since the 2000s.
And I'll just interrupt to say, from my point of view, vCPUs have always been a point of confusion, and I've heard that 2 vCPUs per physical core thing for forever.
Yep.
And all I really care about at the end of the day is, am I using this machine at this capacity, or am I accidentally using it at this capacity, very low capacity? And the best I have from Naomi is just you have to use top to watch your consumption of the power of the machine.
Correct.
That's your sort of one and only tool to do that. And I wish I knew it in more depth, but I wish I was better nerd. But, top is kind of where the buck stops as far as I can tell. Is that a fair assessment?
Kind of. CloudWatch, which are the metrics behind everything at AWS, will show you CPU utilization. Top will tell you if you're maxing out one CPU of a multi-CPU system. And like Linux is going to think that these virtual CPUs are, different physical cores, but you can see, okay, well, I'm running this workload and I have this many vCPUs, but it's only ever using one. Yeah, it's maxing it out, but it's not using the other.
Top won't catch that,
Top will catch that.
or will catch that.
Yeah, CloudWatch won't.
What?
So because that's the OS level. So it's the old kind of symmetric multiprocessing problem where you could have two physical CPUs, not like in the days before multi-core CPUs. You could run an application and it could max out one, but if you didn't write that application to use symmetrical processing, whether it's multi-threading, putting a thread here, a thread here, or whether it's true like using MPI if you're using it in HPC terms, it won't utilize both CPUs.
Yeah, so one will
Same
just
thing.
sit there idle.
Yeah, one would just sit there idle. Yeah, it's all based on the application.
Right, so that's kind of acting as an intermediary between your company's services and a researcher. That's kind of the dumbing down thing that would like to do better, is to tell the researcher, okay, do this magic spell, and to verify that you are using your dollar's worth of compute at the dollar's worth of consumption level.
Yep.
And not at 20 cents, some really low. Okay, anyway, just to put that up.
Can you go back to the last slide?
Yep.
I think I have a sort of sanity check question. So let's say in the top one, C6I, if one series of like modeling requires that they are using multi-processing, right? Then between the both of them, it's no different, right? You would still split the job to each core, and they would both operate at whatever degree of like the task assigned to them. It wouldn't separate CPU 1 versus CPU 2,
no.
Right? You'd have to instantiate, like let's summon 8 threads for, let's say, Python multiprocessing, and then it's just each of them are doing the same job.
Yeah,
it would seem about the same.
Yeah,
but if you're using Dask and some of these lazy computing operations where like you're going to summon all available, it's essentially going to do that top one already. In the C7G example, it's not going to. It's probably just going to use one.
well, you would have to get pretty low level, like way beyond writing Python, whether it's Dask or not, pin something to a specific CPU. Yeah, it's up to your programming language that you choose. If it's using if it's an interpreted language, it's up to that to figure out how it uses threads. Versus if you're writing like assembly or even C or C++, you may have to be more prescriptive about how you address CPU. Yeah.
Which of these would, if somebody was trying to put together a Spark server, would there be any decision difference between the two?
So for Spark, what you should do is, I won't go back to show it, but just use EMR and Graviton's an option.
Elastic
MapReduce, yeah.
Okay. So neither of these. Just
well, no, it's using.
I mean, not Graviton.
Graviton.
Use EMR.
Yeah.
Okay.
If you were running, that's just general, not really process specific advice there. It's more, that's probably the right platform, and that platform does use Graviton if you choose. Yeah. And Rob, to what you were talking about, really, if you're telling a researcher, talking to a researcher, and you're like, hey, you want to make sure you're getting the most bang for your buck, stop with, like, your first stop should be CloudWatch. If you run your job and you look at CloudWatch and it's got 25% CPU utilization, when you were running it, you can say, okay, well, I ran it from 1 to 130 today. You can look at the CloudWatch graph, and if it's like using 25%, then you've way over provisioned. Yeah. If it's pegged at 100% for the entire time you ran your application, you're probably under provision. If you were running infrastructure, like something is up all the time, which is not common in a research workload, we have Compute Optimizer, which will give you these kind of metrics and make suggestions automatically. Say, hey, it looks like this server's been running for this many weeks and it's only ever 25%, maybe that's probably over provision. So here's just a use case example with Graviton 3, load balancing with Nginx. You can see a C6 Graviton versus a C7 Graviton. There are different generations. Parking reminder. Keeps popping up on my wrist.
The prior example was C6I, wasn't it?
Yeah, this is differences between our generations of Graviton.
Okay.
So Graviton 3 Node.js application, C6G versus C7G. Yeah. More fun, perhaps, here. Like Postgres on our Gravitons, you can see it from the C6Gs, a C5 and a C6. So this is confusing graph, but the two in the middle are the x86, the Intel based. The two on the ends are Graviton processors, but of two different generations. So the C7G is faster than the C6I and the C5, which are Intel, and faster than the previous generation of Graviton.
Do you mean to say that all of these are just relative to C6G performance?
That's just what they picked. That's the So MySQL, similar story. Of transactions per minute, C7G, much greater. Like if you look at the previous generation Gravitons and the Intels are roughly equivalent, the C7G is faster and less expensive. FFmpeg, I would argue that if you want absolute performance for FFmpeg, then look at one of the instances I was talking about earlier with video transcoding. Xilinx accelerator built in, or use an FPGA, but that's only if you want like ridiculous performance. Yeah, and I will say that FFmpeg video encoding is very CPU intensive. It'll use all the CPU you have at max speed. Machine learning, Graviton 3 performance increases. So this is all very interesting. This is not the same as what I was talking about earlier with our custom chips. This would be running it directly on CPU as opposed to Trainium, our Trainium ASICs. So Graviton 4, latest generation. We're running out of time, so I won't belabor this. But you can see the specs there. So 96 V2 cores, 2 meg of L2 cache per core. There we go. Necessary animation, but this is our latest Graviton 4s. So 50% more cores per socket than 3, support for coherent multi-socket, and a single system with up to 3 times more core than Graviton 3. This is kind of hard to see, these graphs. So like I said, I'll give everyone the slide deck so you can see. The color choice wasn't great, and I did a terrible job trying to change the colors. I am not a designer.
What is this?
These are benchmarks for different applications.
Oh.
Yeah, like I said, it's very difficult to read on a projector. On the screen on a laptop, it's not so bad. But yeah, plus 40% MySQL performance. And you can see the big leap between Graviton 3 and 4. You can see the hardware differences between 3 and 4. So there is documentation of how to get started, and we have tons and tons of examples and help that can enable you to, if your application you wrote yourself, you want to compile it for ARM, we have resources to help you. So, interpreted and compiled bytecode languages can run without modification. So Python itself it has been compiled for ARM, it can run on Graviton. Your Python code doesn't really know or care that it's running on, whether it's running on ARM or any Intel-based x86 processor. So yeah, your Python generally will run a Graviton instance without modifications. Compiled applications, so like I said, like Rust, Go, C++, C, yes, you're going to need to port your code. Yeah, we put the big caution there. We typically it just works, but give it a try. Most major Linux distributions, so of course Amazon Linux, Red Hat, CentOS, Ubuntu, Debian, all have versions for ARM, which will run on Graviton. Yep. So if you wanted to run, if you want to run FreeBSD, you can run FreeBSD on a Graviton. For all of the BSD fans in the audience. Yep, lots of stuff runs on Graviton processors and works with our Graviton systems. ECS and EKS, this is kind of redundant, we already talked about it, but ECS and EKS, which is our container management infrastructure, you can run Graviton-based containers. All these orchestrators work, so ECS and EKS, Docker, Kubernetes, all work with ARM processors, which means they work with Graviton. So, I just give you more information on those. Same thing with Lambda. You can say your task, when you're setting up your task, you could tell it, all right, I want to run this on Graviton and x86 instance. So, yep. Porting advice, I mentioned earlier, the GitHub for help with porting your applications. Again, yeah, identify all libraries and dependencies and agents in your production environment. Get started with that. Then once you know what you're actually using to run your application, then you can see if those libraries, if there's a version that will work on ARM, and then you can port your code using some help to ARM and then run it on Graviton. Like I said, these are very text heavy and there's links in them. So I will, of course, give you the slide deck. ProServe and partners. So if you had an application that this is a little more commercial than research focused, but if you had some big application that the whole institution ran on and you wanted to recompile it for ARM, there are partners who specialize in that. And there are commercial applications that work, so like Datadog, Databricks, those work on Gravitons. Cool. So that was it. Before we get into questions, I will pull up the. Here we go. Don't worry about this. Just be getting into my internal account. Go to RDS. Say I'm going to launch a new database. Engine. Instance configuration. So like, okay, yeah. The default is a graviton. And this was MariaDB. So yeah, it works. So if you were launching like Aurora, Postgres compatible, scroll down here, instance configuration. Yep. So an R6G. So you'll see like these don't have the G, these are all your Intel based. And all of these options have the G, those are all the different permutations. So you have like 8 virtual CPUs and 64 gig of RAM, all the way up to 64 virtual CPUs and a terabyte of RAM for your Graviton-based EC2 instance types for RDS or Aurora Postgres compatible.